Good morning and welcome to this Nexperia Power Live event. You've joined us here on our automotive channel. We are very much looking forward to discuss and share with you a number of design and technology insights. Let's open with our new Silicon Germanium rectifiers. It's not every day that the use of new materials is announced, but this is actually what we did with this novel diode technology that comes with an enhanced safe operating area and is ideal for high-frequency converter applications. This particular session is scheduled for 25 minutes. We will begin with a short overview of the topic and then follow with open questions and answers. So please join in. All contributions are anonymous. Feel free to ask any questions to our experts, but also share your own knowledge and experiences. Questions can be asked throughout the session by using the orange speech bubble in the bottom right of your screen. Today's presenters are Reza Betash, who is Application Marketing Manager, and Ali Anaisi, who is PhD candidate at the Helmut Schmidt University in Hamburg. And with that, I will hand over to Reza to begin.
Thank you very much, Judith. So this is the agenda of the talk today. The presentation is split up into two parts. I will start with a short introduction into the internal structure of this new technology, of the Silicon Germanium technology, and I will explain to you the value propositions which come with this technology. One important point is the extended safe operating area, and then I will hand over to Ali. Ali is from the Helmut Schmidt University in Hamburg, and we teamed up with the Helmut Schmidt University, especially with the department of Professor Hoffmann, who is specialized on power electronics. And Ali will explain to you the measurements and the characterizations he did on the Silicon Germanium rectifier in terms of reverse recovery and also its usage in a DC-DC converter. So let's start with the structure of Silicon Germanium. What you see here is the very simplified cross-section of the Schottky rectifier on the left-hand side and a Silicon Germanium rectifier on the right-hand side. So you see in case of the Schottky rectifier, we have the Schottky metal on top, and the work function of this Schottky metal will define the barrier height seen by the electrons, and the light green area is the drift region for the carriers, and the dark green is the substrate. In contrast to that, we have a very thin silicon germanium layer on top of the silicon germanium rectifier between the metal and the drift region. And this very thin layer enhances the current contribution coming from a diffusion current. That means compared to a standard PN junction, the silicon germanium device has a higher current density thanks to this diffusion current compared for a given forward voltage drop. And at the same time, since it is a PN junction, it has the low leakage of a recovery rectifier. So important to note that silicon germanium is kind of a hybrid technology between Schottky and a PN junction. And this results in several value propositions, which you can see on this slide. So as I mentioned, it has a low VF. It's more or less comparable to a Schottky device, but at the same time, it comes with a low leakage current and with a high thermal stability like a recovery rectifier. And this enables the power electronics designer to have a robust design in terms of thermal stability. So he doesn't need to care too much about thermal runaways and things like that, which come usually with Schottky devices. So silicon germanium is really the right choice if you have a high ambient temperature. And Ali will also explain to you later on that also the switching behavior is excellent. And beyond the electrical characteristics, our products, or also the silicon germanium products, of course, will come with a 2 times AEC-Q qualification. That means we have qualified the products twice according to this automotive standard. So they are really very robust. And the current reverse voltage range is between 120 volts and 200 volts. And by using this very efficient clip-bonded flat power package, they also come with a very rugged behavior against surge currents. And you can also have some space saving on your PCB. Okay, and one important point, as I mentioned at the beginning, is the extended safe operating area. And for that, I would like to show you a short movie. You see two devices, one Schottky device and one Silicon Germanium device, biased in reverse current, in reverse voltage, and they are put down upside down on a thermal chuck. And now we increase the temperature of the thermal chuck. So the x-axis is the temperature, and the y-axis is the reverse leakage current. And you see that the Schottky device runs into a thermal runaway at a given point, while the silicon germanium rectifier continues and there is no thermal runaway. By the way, you see also that the leakage current of the silicon germanium device is orders of magnitude lower than the Schottky counterpart. Okay, and with that, I would like to hand over to Ali for the measurements.
Yeah. Thank you, Reza. Welcome, everyone. My name is Ali Anaisi, as already mentioned. Today, I will talk a little bit and present you a thorough investigation that we did with the SiGe diode. We did a comprehensive benchmarking, and one of the characteristics that we tested was the switching characteristic, in fact. We used a pretty standard double pulse configuration, as you can see on the left side of the slide. And the PCB is in the picture below in order to test the reverse recovery. And consecutively after that, we wanted to test the SiGe diode in a realistic applicative manner. So we tested it or implemented it in a DC-DC converter, as you can see on the right side. It's also standard buck converter topology, but we focus really on this automotive sector in the 48 to 12 volt region and tested the efficiency, compared it with other diodes. As you can see here, you have the plot of the measurement, the results that we have from the double pulse testing. Here we are comparing a SiGe diode with a Schottky diode. The orange curve is the SiGe diode, the blue curve is the Schottky diode. To be exact, it's a planar Schottky diode. And first, the crucial condition that we tested in was a fast switching, high frequency environment that we wanted to put the SiGe diode in. And you can see that the slope of the current that we used here was didt of 1 ampere per nanosecond, or DIF dt of -1 ampere per nanosecond. And just for reference, what is usually put in the data sheet or tested in the data sheet is a didt of 0.1 or 0.2. So we are 5 to 10 times higher than what you would normally see in the data sheet. And what you can see here, really in terms of the parameters that we analyzed, we looked at the QRR, which is the reverse recovery charge, and the IRM, which is the maximum reverse recovery current, basically the negative peak you see. And both of those parameters, the SiGe comes out on top, as you can see in the picture. It has a lower peak as well as a lower QRR. We quantified these results, of course, in terms of numbers. So we have a table on the left side. As you can see, we tested both temperatures, 25 degrees Celsius and 150 degrees Celsius. And what you can see in the terms of numbers is really that the SiGe is significantly lower also in terms of TRR, which is the reverse recovery time. So not only the switching process is shorter, but also the charge involved, which is the main contributor to the switching loss, basically, is lower. And this still holds for 150 degrees Celsius. The IRM, the reverse recovery current peak, remains stable for the planar Schottky diode while it increases for SiGe, but nevertheless, the QRR remains significantly lower, which also means a lower loss in that sense. So it can basically conclude faster switching times, lower switching loss, which means then even for higher temperatures, better reverse recovery current. So in order to verify those results, in order to see if it's plausible or not, we wanted to investigate the SiGe diode in a DC-DC application in order to see if we can reproduce the benefits of the switching losses or the benefits of the better switching performance. And what you can see here is, as already mentioned, the DC-DC converter. We used the diode here as a freewheeling diode. And what we did is we varied the switching frequency actually to see the influence of the switching loss and the switching performance. And you can see the efficiency values that we compared with the same Schottky diode. Just to mention, they were in a comparable range in terms of rating and voltage and current rating. And what you can see here for 130 kilohertz, the difference is very slight. So the reason being is that here the conduction losses take over. They are the main part that takes place for the total losses. So you could even say, maybe argue that the difference is measurement noise. And in order to test the switching performance and to verify it, we increase the frequency. And you can really see that with increasing the frequency over 250 kilohertz up to 500 kilohertz, you see that the difference becomes bigger and bigger. The reason being is that the switching losses take a greater part in the total loss equation. So in terms of numbers, when you increase it to 500 kilohertz, you reach a difference from, which was very slight in the beginning, to up to 1% between the SiGe and the Schottky diode, with SiGe being on top on that. So you can say high efficiency and SiGe is fit for a high frequency operation. Yeah, just a little self-advertisement here. We, throughout the collaboration of Nexperia and the Helmut Schmidt University, where I'm from, we could produce 2 papers that were published in 2 conferences. One is the PCM Europe 2020, which is basically the digital days, which takes place next week. And there I will present the benchmarking, the comprehensive benchmarking, also including things like conduction and blocking characteristics, leakage current, etc. And the DC-DC converter and its efficiency analysis, also looking into things like surge current, is something that I discuss in a paper that is published in the PCM in Asia, which now takes place in November 2020. And yeah, you can meet me there also on the digital days next week to have a further discussion. So yeah, thank you for your attention. Feel free to ask any question using the chat function below. And yeah, I hope for a fruitful discussion.
Thanks, Ali. Thanks, Reza. Let me quickly remind the audience, if you like to ask a question, please use the orange speech bubble in the bottom right of your screen. And now let's start, as I already see the first questions coming in. So I think this one is for Reza. What are potential applications for silicon germanium rectifiers?
Okay, this is a very good question. So I think the first one is very obvious. So as mentioned by Ali, we use it in a converter, in a high frequency converter. And you see the advantages coming from the high or the efficient switching behavior. So everywhere where you need a high thermal robustness and low leakage current, combined with a high switching frequency, is the right application for silicon germanium. I have prepared some backup slides. Let me check. Okay. Okay, for example, LED lighting, as you can see here on this picture. LED lighting is a high power density application with a high ambient temperature. You have a high switching frequency. This is a simplified schematic showing a boost buck converter. And silicon germanium would be the right choice here, since you have a high thermal robustness. So you don't need to care about thermal runaway. And at the same time, as explained by Ali, you wouldn't sacrifice any efficiency due to high losses. Or we have also this application. This is an engine control unit. This is an application coming from one of our customers from automotive area. And this is a solenoid driver schematic. And the point is that you need a very low leakage current, since this is an automotive application and the board is in the engine bay of the car, so the ambient temperature is high. And usually recovery rectifiers are used here. But at the same time, recovery rectifiers come with a high forward voltage drop. So you have a lot of dissipated power in the package. And by using silicon germanium rectifiers, you would have the thermal stability, but you would at the same time reduce the forward losses in the device. So this is just a few examples which I can mention. There are many.
Okay, thank you, Reza. The next question is actually two questions. So we'll read out. Did you compare silicon germanium with PN diodes in a similar specification range? And if yes, how does it compare in terms of thermal behavior?
Ali, do you want to answer that? Yeah. Okay.
Okay, I think I can take this one.
Yeah.
Tested also other PN diodes, like I already mentioned. Hello?
Yes.
Yeah.
Okay.
So I hope you can hear me fine.
Yes.
All right.
Go ahead.
So we tested also the PN diodes and compared the SiGe with other PN diodes in a comparable range. This is something we did in the comprehensive analysis we did in the project. Like I said, it was way more than switching performance that we tested. And yeah, and the results that we have in terms of thermal behavior, I mean, it really depends from what angle you look at it or what application you are in. For example, in the DC-DC operation that we had, due to the higher switching losses that the PN diodes have, we reached a thermal runaway pretty quick by increasing the frequency for the PN diodes, while the SiGe diode could still compete with Schottky diodes and be stable, where you normally think that PN diodes would be the choice to pick for high thermal strains. So basically, if you see the comparison Schottky versus PN, you would pick PN for their leakage currents. This is one of the main reasons, I think, or one of the main weakness of Schottky. And I would say in that sense, this is where SiGe really cuts in. With the low leakage currents, it could still provide while having a beneficial switching performance. And so any application where normally a PN would be picked, where the leakage currents are of high importance, for example, this is something where SiGe is also a considerable choice. I think we have an example here also in the backup slide. Reza, could you open the reverse polarity?
Okay. Yes. This is a good example. Okay.
Yeah, exactly. We have here reverse polarity protection. So basically, there are some conditions that need to be met for the leakage currents. Needs to be below a certain threshold for a specific temperature. And this is something that the SiGe really can provide. As throughout the investigations, we could show that SiGe could even surpass, or how do you say it, surpass or even undergo in that sense, or show a lower leakage current than PN diodes, depending on the temperature and the operating condition, of course. And this is something that could be beneficial in an application like this, for example, where you have sensitive electronics on the other side of the polarity protection, where the leakage currents have to be kept minimal. So in that regard, yes, we compared it with the PN diode, and in terms of the strength that the PN diodes are picked for usually, I think SiGe can still compete and be a considerable choice in applications in that regard.
Super, thank you, Ali. Next question. Does low QRR have any advantage on EMI emissions also?
I would say not necessarily. Ali, do you want to add something?
I would say the effect of the low QRR on the EMI is not directly because the EMI is mainly a result of oscillation, ringing, and the peak that we have, the amplitudes of the peak. But EMI in general is also could not only be traced back to the diode, it's always a conjunction of the application you have. It's very individually. So you have a switch, for example, in a DC-DC converter, you have a conjunction of the switch and the diode working with each other, and the EMI is always a result of the total environment that you put the SiGe in. So I would say the benefit of a lower QRR, it would not negatively affect EMI in that regard.
Okay. Next question is, how does the chip size of SiGe chip vary with respect to conventional Schottky diode?
This is a very good question. So, okay, so you, excuse me. So you need to take into account which Schottky diode you compare to silicon germanium. So obviously the barrier height of the Schottky diode is important. The lower the barrier height, the lower the threshold voltage, the forward voltage drop. But let's assume a barrier height of, let's say, 0.7 electron volt. And the Schottky diode has still a higher current density compared to silicon germanium. But the point is, the current density for a given forward voltage for a PN junction is much higher. So silicon germanium is in between the PN and the Schottky. So that means the die size of the silicon germanium is slightly bigger or comparable to a Schottky, but significantly smaller compared to a PN junction. I hope this answers the question.
Okay. Let me go swiftly to the next one because we have quite some coming in. So what is the TJ max for the silicon germanium diode?
They are all automotive qualified 175 degrees C, and they are even twice qualified according to AEC-Q standard. And as I showed you, you can really almost go up to the maximum junction temperature with the silicon germanium device without thermal runaway.
Okay, super. Thank you, Reza. The next one is also about automotive qualification. So what does it mean 2 times AEC-Q 101?
That means you are testing twice the time you would usually test. For example, there are requirements regarding the temperature cycling. So the device has to withstand a number of temperature cycles of temperature. And I think the standard AEC-Q is 1,000 cycles. We go for 2,000. And the same also for example, for high temperature reverse bias tests. You have to qualify the product for a given time in reverse bias. We go beyond that time. So it is really twice the time. This is the meaning of that.
Okay. The next question is, can this technology also be applied in the MOSFET structure to improve the substrate diode behavior?
This was indeed tried in the past. So silicon germanium is already used for heterojunction bipolar transistors, and also MOSFETs were realized, but the AP layer necessary for MOSFET is very demanding, and therefore they didn't make it. So I would say not that easy, no.
Okay. We have time for, I think, one last short question. This is a commercial one. So what will be the price of silicon germanium diodes?
A very good question that comes up every time. So obviously, there will be a premium, I need to admit, but it won't be an order of magnitude. Okay, so it's not in the same range, but there will be kind of premium on silicon germanium, but not factor 2 or something. But there's a small premium to pay.
Okay. I think that brings us to the end of the session. That's all the time we have. Thank you, Reza, and thank you, Ali, and thank you to everybody who contributed. If you have further questions, don't hesitate to access our live chat. You can also take a look, of course, below the video screen. Then you will see download links for further information, such as the opportunity to order samples of our new Silicon Germanium rectifiers, or links to a landing page where you can download data sheets, and also have a look at a quick learning video that dives a little bit deeper into Silicon Germanium technology. And in approximately 5 minutes, we will begin our next live session on technologies for automotive 48-volt hybrid. So if you have a little bit more time today, please do stay.